Hey there, welcome to Chapter 9, 9.1 actually, and we're going to start talking about cellular respiration. And so these notes are just on the redox portion of this. So let's get started. So remember that life is work. It's constantly, so to keep us alive, we are in constant need of energy. And energy is used to recycle matter into many different molecules. So we take in energy, and that is what allows us to move molecules around. It allows for nutrient cycling. And so it's the interplay of respiration and photosynthesis that are prime examples of this work. So it's the light energy from the sun that allows us to take the carbons and the hydrogens and the oxygens to put them together. It's the energy from our food that allows us to take those carbons, hydrogens, and oxygens apart and to release carbon dioxide and water. So it is energy that fuels the nutrient cycles. And so during photosynthesis, energy is added to the system. So let's just go back to a little Gibbs free energy and remember that respiration is catabolic, meaning that it is breaking down. It is exergonic, meaning that it is releasing energy. And that it has a change in free energy, or a negative G, of 686 cals per mole. And so remember that the negative G means that it's spontaneous or endergonic. And so that once the reaction is initiated, it's going to proceed without the input of energy. And so respiration and fermentation are similar to combustion. So think of respiration as like a burning match. So organic fuel, the carbons, the hydrogens, the oxygens that are in the match are going to combine with oxygen in the atmosphere. And at the end of it, we're going to produce heat and carbon dioxide. And so respiration, however, is a much slower and controlled burn than is lighting a match. So it's a series of many chemical reactions that slowly release energy, that slowly releases the carbon dioxide, that slowly releases the heat. Otherwise, if we burned up as quickly as a candle or as a match, we would burn up. So we have a slow burn. And so remember that the energy is removed by breaking bonds of O2. Lots of energy in O2 and moving around the electrons. This is the basis of redox. So redox is the reduction, R-E-D, redox, and the oxidation of molecules. So reduction and oxidation. And so during oxidation, a molecule loses electrons. So remember that oxidation is loss. Oil. Remember oil rig. Oxidation is loss, while reduction is the gaining of electrons. Reduction is gaining. And so this is counterintuitive. If it is gaining an electron, it is being reduced, and that trips everybody up. But so the wording is counterintuitive, but I like to think of it like this. As you gain electrons, you're gaining a negative charge, or your charge is being reduced. So if you're being reduced, if a molecule is being reduced, the charge is being reduced. As you gain electrons, your charge is being reduced. So here A is giving the electron over to B. So A is losing an electron, so therefore it is being oxidized. Oxidation is loss. B here is gaining an electron. So B is being reduced. It is gaining a negative charge. It is being reduced in charge. So let's look at an example of this. Salt is ionically bonded. And so it is a positive and a negative charge attracted to one another. So here, Na plus Cl makes NaCl. And so it becomes positive. So the Na, or the sodium, becomes positive. Therefore, it lost a negative charge. It is oxidized. It lost an electron. It is oxidize. Oil, oxidation is loss. It lost an electron. The chloride or chlorine becomes negative. So therefore, it has gained a negative charge. It has gained. It is reduced in charge. It is reduced in charge. So reduction is gaining. Rig, oil rig. So biologists identify redox a little bit differently than chemists. And it's simply because in the scope of this class, in the scope of intro biology, we're looking at basically two equations, and that is going to be photosynthesis and cell respiration. And so we can look at it a little bit differently. It's the same and it's different. So oil, oxidation is losing hydrogen atoms. It's going to be the same thing. And reduction is gaining hydrogen atoms. Let's look at what I mean by this. Remember that the electronegativity of hydrogen is weak. Everyone is going to hog hydrogen's electrons. So anything that's paired up with hydrogen is going to eventually hog or pull those electrons away. And so we're looking at redox a little bit differently than chemists do. We're looking at it as partial charges. And so here, if we look, the C, the carbon, is stronger than the hydrogen. So when it loses its weak partner and bonds with strong oxygen, so here, when the carbon is then going to be bonded with oxygen, the oxygen is going to be way stronger than the hydrogen, and so it's going to pull those electrons towards it. And so therefore, the hydrogen, it's lost hydrogen. This carbon has lost its hydrogen. And so therefore, it's been oxidized. If we look, this carbon has lost its electrons. It's moved further away from the carbon. The electrons moved further away. These are the partial charges. The electrons have moved further away from that carbon. And so therefore, oxidation is lost. The carbon has lost those electrons. So let's look at this a little bit more. Let's keep thinking about this. Remember that the electronegativity of H is weak. Everyone hogs H's electrons. Remember that. So the O2, let's look at O2. O2 is a very stable molecule with lots of energy. It is sharing those electrons evenly, and so there's lots of energy in there. When oxygen is pulled apart and paired with hydrogen, so here we're looking at the H2O and it's paired with hydrogen. Well, H is very weak, and so therefore those electrons are going to be hogged by the oxygen. Think water is negative, and so, or not water. Think of water. The oxygen is slightly negative. And so here the electrons are spending more time around that oxygen, and so it makes it slightly negative. And so remember that oxidation is loss, but now this oxygen is being reduced because it is gaining hydrogens. It's gaining those weak hydrogens, and so therefore it is gaining these electrons because the hydrogens can't hang on to those electrons. And so the oxygen has been reduced to water in a partial charge. So glucose loses hydrogen atoms. It is being oxidized. Let's look at this. Here we go. We have carbon, hydrogen, and oxygen. And so this carbon dioxide has lost hydrogen atoms. And so therefore, it has oxidation is loss of hydrogen. And so therefore, it is being oxidized. And so the O2 is gaining hydrogen. And so therefore, it is being reduced. Remember, reduction is gained. So organisms often breathe oxygen because it has so much potential energy and it is stable. It has lots of energy to give. And remember that materials with lots of hydrogen atoms, methane, glucose, are great sources of fuel because they have lots of hydrogen that give and make everything less stable. So we need that hydrogen to bond to stuff to make things less stable. So if glucose is being oxidized, something must be doing the oxidizing. So if glucose here, we can see, is being oxidized, then what is doing the oxidation? It is the oxygen. And so if oxygen is being reduced here, the oxygen is being reduced, something must be the reducing agent. And the only thing that is in the equation that could be doing the reducing, it is the glucose. Glucose is the reducing agent. And so combustion and respiration are spontaneous reactions. And methane requires activation energy, just like striking a match does, in the form of ignition temperature. And it'll spontaneously continue to burn down a whole tree. Organisms do not require ignition temperature. We would burn up. To break down glucose, we have enzymes that lower the activation energy. Okay, so what I want you guys to do to sort of solidify this is work on the notes assist that I have incorporated on our Unified Classroom page or on our class page. Okay, have a great day.